Hi, everybody. Welcome to this program from the Dask Distributed Summit. This is Dask in the high energy physics community, and we'll be having a workshop mainly sort of hosted and facilitated by Oksana, Shadura, and Lukas, Heinrich. I will let them give a further introduction of what we'll be talking about today and how this is all going to go, but thank you for joining us, and please enjoy.
Thanks, Stephanie. So I think I will just add a couple of words. Basically, I think what we wanted to do is try to understand what is the usage of Dask in our community, particularly between different experiments, facilities, try to understand use cases, and maybe just talk between each other, like, to have some understanding where we want to move, which features we are missing. And for example, my personal interest is interactive scale-out systems and how we can actually integrate it in all the like our federated scientific grid computing infrastructure. So yeah, and Lukas, do you have a couple of words?
Yeah, no, I think I don't have too much to add. Thanks everybody for joining. I think it's early days for Dask and high energy physics, but I think also given the rest of the Dask summit, it's clear that it's kind of a quite interesting technology. And yeah, so generally kind of, I think our usage patterns somewhat map well onto Dask, but I mean, there are definitely some high energy physics specific issues. The first of all, which Jim was going to talk about adding a new collection type, because it turns out our data doesn't fit the basic, like the standard Dask collection types of array or bags. And yeah, so I think I don't have much further to add, so I'm happy to give Jim the floor. Jim, I guess you can just share the slides, right?
Okay, yeah, I can do that. Yeah. Is that working?
Yeah, that works. Thank you.
Okay. So, yeah, so I'll be talking about future plans, but near future, to integrate two libraries, Awkward Array and Dask. And since this is the first talk of the HEP session, and I expecting and hoping that that people from different communities are meeting each other here, I start with some introduction to what we do in particle physics, which also motivates why we have this different view of data that we want to integrate with Dask. So I can motivate with a very old example. This is from 1964. It's a photo of a subatomic particles leaving tracks in a detector. And I can do that because even that long ago, it illustrates all of the basic issues that we have in high energy physics. So a group at Berkeley scanned through 100,000 photos to find this one. So first of all, large number of events to scan through. And to find this discovery of the omega baryon. This was a big deal. It cemented the discovery of quarks. So the question is, do you see it? You look at this image, and I think most of us here, even trained particle physicists, are not going to see it without green lines on top of the actual event, and that is the event topology there. That's what happens when the particles collide. Which ones are which new particles are created, how they decay, how they decay, how they decay, and it looks like that in the actual event display. So this is what particle physicists do: collide particles, produce new particles, and take pictures of the decays. However, these pictures come to us unlabeled. So there's lots of interactions overlapping the interesting ones, especially now that the data rates are so much higher. This is not unusual event display. So modern particle physics just scales this up. We've gone from photographs to digitized scans, 100,000 events to trillions of events, manual and semi-automated scans to algorithmic searches and machine learning. And the number of authors is also ballooned. It's the same idea, but scaled up. So we've been doing it for a long time, actually. And so the key thing about this is that combinatorics of more than one, many variable length collections is crucial. in order to find that event, you had to do things like looking through all of the observed particles, find opposite sign pairs of electrons consistent with a photon conversion, blah, blah, blah. So that you go from the observed particles walking up the decay chain back. And those going through the observed particles, you have to search everything in the event, but not anything in the next event. So there's a certain opportunity for parallelism there. So each of the events has a different number of each type of particle, and this is not reducible to a flat table without padding or loss. So whereas some communities are turning things into rectilinear tables as a pre-analysis step, for us, the analysis itself really has to be with the variable length structures. And so that's what the awkward array library is for. We're trying to analyze these data as arrays, and in order to do so, we needed arrays to be able to deal with nested variable length data, arbitrary length lists, records, mixed types, missing data. And we want to do it all as a strict generalization of NumPy, so that anything that you learn about from NumPy on like Stack Overflow will apply to awkward arrays. So let's just give a code example before moving on to Dask. Here I'm just loading two arrays just by iterating Python objects. And you can see that the lists are variable lengths and they're not the same lengths. The list of strings and the list of numbers. And we can say things like octet combinations of the first array. And so we're looking for two-fold combinations or maybe three-fold combinations. We can say Cartesian products of 1 and 2. And actually, there's a whole lot of these octet star functions, octet this and octet that, some of which are strict generalizations of NumPy, and others are completely new, not even in NumPy, like these. So can awkward arrays fit into a Dask collection? So Dask has 3 basic collections: arrays, data frames, and bags. And awkward arrays kind of fit here. A bit like an array, a bit like a bag, and not really like a data frame. So they're like arrays in that the elements have a single type across the array, rich slicing semantics, and compiled loops for speed. They're unlike an array in that the type can be nested, variable length, nullable, heterogeneous, blah, blah, blah. Also unlike arrays in that partitioning only makes sense in 1D because after 1D, it might not be regular. And there are fundamental functions beyond NumPy. It's like a bag in the type generality and the 1D partitioning, but it's unlike a bag in that it has a single type, rich slicing and access concept and compiled loops. And it's not really like a data frame at all because it doesn't have 2 things that are key to data frames, an index and columns. So the nearest equivalent of columns in an awkward array are record fields if you happen to have record structure at the top, and the previous example didn't. So the best fit is Dask array, but it's not a perfect fit. So we have tried this quite a lot, years of trying this. Can awkward arrays be Dask arrays? One of the first thing is that the slices and functions named octet star are the fundamental operations of awkward array. Just as slices, np.star, and ndarray methods are in NumPy. But we want a DAG of like the octet star nodes. That would be the right starting point for optimization, not the way that they're implemented in NumPy. Awkward arrays don't have a shape and a D type. That is a factorization that only applies to rectilinear data. You quickly run into Dask.array operations that expect them to. And Uproot's Git history is littered with examples to try to make it work. Really, at least 3 years, we were trying to make Dask collections in Uproot, and it just doesn't fit. So awkward arrays, if it's going to be in the Dask, like a Dask collection, it has to be a new collection type. So awkward array has some delayed types features that we can use for that integration. So namely, these are partitioning and partitioned arrays and virtual arrays, which when you put those 2 concepts together, you get a standard lazy array. So for instance, you can have a function that reads one partition, and you can make an array that is a bunch of partitions of virtual, of calls to that function. And then whenever you look at, you look at a slice of this, it'll read what it has to. It'll read a partition that is necessary to deliver that data. And then if you look at more, it'll have to read more. And if you look at the whole thing, it'll have to read the beginning and the end, because that's how we print stuff out, with a dot, dot, dot in the middle. So looking at this in the low-level view and the array's layout, this is done with the two node types called a partition array and a virtual array. So the virtual array holds the function and the form or type, and the partition array is just many of them. So the properties of these node types is that partitioned array can only be at the root of awkward array's tree structure. And partition sizes must be known. So that's what makes partitioning a one-dimensional thing. You can't have partitioned arrays of partitioned arrays. The virtual arrays are allowed anywhere in the tree structure, including nested. You can have virtual arrays of virtual arrays, and that is actually useful. There's a form, which is a detailed type information, and length are optional but recommended because it materializes this data. There's calls the function to read it as soon as an operation needs to know that information. So the more information you can give it, the later it can materialize. Now, that is the key difference between these things and what Dask does. So Dask asks the user when to evaluate. So if I were to do the same thing, making using Dask delayed in order to create an array of partitions of virtual partitions and do exactly the same thing, it doesn't read until you say .compute. That is the user input, where the user gets to say when the materialization happens. And awkward virtual arrays don't. They just materialize as soon as you need the information, because the rest of awkward arrays structure, the infrastructure is all eager. So this means that there's like a spectrum of transparency. Coffee and uproot, which is what we use now primarily, they make users think about one partition at a time. Dask arrays evaluate when the user says go, and virtual arrays evaluate as needed. And that Goldilocks median is kind of ideal, where you don't have to think about exactly how something is chunked, but you get to say when the read happens, so it doesn't accidentally happen. Another thing that we want to be thinking about when integrating awkward array and Dask is that awkward array has multiple levels of abstraction within the library. There's a high-level view, which is entirely in Python, and these are the awk.star functions. And like I said before, it'd be really nice to have a DAG of those functions. There's a mid-level, which is currently C++ and Numba, two implementations of it. And it has a low level, which are called kernels, which only take one-dimensional data. We might want to have a DAG at any one of these levels for the motivations I'll describe on the next page. And the low-level DAG would only be possible if we convert our C++ classes into Python classes, which is a thing that we're thinking about doing for other reasons. But that's part of the mix of thinking about how we're going to integrate these libraries. So then motivations is my second to last slide. Motivations is my second to last slide. The use cases for a DAG are distributed computing, obviously. And this could be useful at high or mid-level. And it may leverage virtual array or partitioned array to internalize Dask the way that Xarray does, or not. These are all questions that we're thinking about now in the early design stages. But we wanted to be clear how to use Dask monitoring tools in either case. Using subgraphs that are independent of event number would be an important optimization, because remember, we have embarrassingly parallel independent events. But there's other things that we can do with a DAG other than distributed computing. Static analysis, it would be very useful to identify which fields a block of code, which record fields a block of code will access, so that you can bundle requests for it up to front, requests for those columns up front. So that's especially good for high latency networks. Another is for streamlining GPU code. And this would only work if we can go all the way down to the low level. All of the kernel functions will eventually be ported to CUDA so that we can run awkward arrays on CPUs and GPUs. But we don't want Python calls to be synchronization points between calling the kernels. And so for that, we want to be able to give CUDA a DAG. And the best way to give CUDA a DAG of operations to perform is by creating a DAG in Dask and then converting that DAG. So actually, we have a lot of reasons other than just distributed computing why we want a DAG and currently don't have one. So in conclusion, particle physicists and probably others, although I didn't talk about it here, need large variable length collections. Large collections of variable length objects. Despite virtual array and partition array, awkward array lacks a DAG representation, which will provide more control over distributed computing and other applications. Awkward arrays don't fit into Dask arrays. We tried, we really did. And so we're pursuing a project to develop awkward Dask collections with Anaconda. And some really basic questions are still on the table, like at which level of abstraction. There are reasons for high level and reasons for low level. Kind of be nice to do both, but in order to do the low level, we have some refactoring to do. That's it for me. Questions?
Yep, anybody has a question? Did you?
Oh, I can't see the chat, so
I guess I could have a comment. As much as I love virtual array and the sort of just-in-time access, it seems very clear, as you put out, in the previous slide, that without building a DAG up front, you really just don't have the opportunities that you would have to optimize your storage access, which is one of the biggest bottlenecks in this whole business. So I think without a doubt, we really do have to walk away from this just-in-time and go towards DAG, even though it does require, as you know, a huge, huge refactoring of how the awkward operations are built.
Yeah, keep in mind for the motivation of distributed computing, which is the motivation you're talking about here, it only has to be at high or mid-level. And that is possible without refactoring. The low level would be required if we're going to make a CUDA DAG.
Even for field, figuring out what fields are going to be accessed, I think you would have to be at least, have to change the C++, or at least put into C++ something that would track what the type is of the operation without evaluating it.
You need to look in the DAG for the get item calls. When get item has a string in it, then you know that you're getting a record field relative to whatever level of record that is. That virtual array needs to have a form so you know what level of record that is. But that makes it doable actually at high level, because get item is a single operation at high level. So I think that would be possible, but yeah, actually we want to do the low level thing, but yeah.
So I have a comment or a question. So it seems like there's been a lot of, so great talk, by the way. It's really fun not being a particle physicist, listening to you all talk. This is the best part of the job, is getting a lot of exposure to different groups. If I were to summarize on the technical side, it's like we tried for a long time to make this fit into Dask collections. It didn't fit. So like maybe we need to go and make a new collection. That sounds great. Like making new collections is part of the design. I'm hopeful that it's actually relatively easy and relatively cheap to make a new collection. We've seen this in some external projects. So like X-Ray is an example of an external Dask collection, although I kind of use some Dask collections internally. There's Dask GeoPandas, there's Rapids, there's probably some others out there. Like that was an interface that was designed to be used externally. And so I'm hopeful that is the right choice for you all. I'm also hopeful there's a lot of stuff that you can reuse to make that an easy thing. But maybe that was more of a comment than a question. I think all people are guilty of this. But if I were to try to turn that into a question, it would be, well, what was hard about making your own collection? Like, why wasn't that the first thing that you tried?
Why was it making our own collection the first thing?
Yeah, or like why?
Oh.
Like it seems like you've been resisting that as an approach.
Oh, actually, on principle, just because we think it's better to reuse than invent. But so actually, I felt we had to justify going and making a new collection.
Okay, well, it seems like we've all learned that is not necessary.
It was practical too, is effort. Certainly, if it was shown that we could reuse it, the effort level to implement would be less, and the maintenance effort would be less.
Yeah, no, I get that. I guess my sense. So that will be true if there's lots of complicated parallel algorithms that you're going to need. So like if you're doing matrix multiplies, for example, like you're going to want to reuse the Dask array stuff because that's really complicated.
Yeah.
If you're just doing a bunch of embarrassingly parallel stuff, like there's stuff to reuse, like blockwise is probably a good operation, which is collection agnostic, which will like do all of the embarrassingly parallel and broadcasting stuff that you probably want to do. But
okay.
Yeah, I'm hopeful that I'm hopeful you can squeeze out an awkward collection that just does embarrassingly parallel stuff in a day.
Well,
right?
so,
and adding more stuff will be harder.
I mean, I kind of did that once already. The problem is you don't keep track of the type as to the level that we'd like. With Dask array, any amount of delayed operations you do on that, you still know sort of the basic features of the output, right? You kind of know its, I mean, its shape and its D type, right? And that's very nice and, helps users understand because, if you're doing a bunch of delayed operations and you don't actually know what you're going to get, or if it even works until you type compute, that's kind of a pain point, right? And for awkward, we'd have to go through all that same business of tracking what these manipulations are doing to the high level type.
Yeah.
In such a way that we can present it to the user, and the user can be reasonably assured that by the time they type that compute, there wasn't some mess up, 10 lines above that will make the DAG fail halfway through.
Yeah. And
if you need that, then that's a lot of work. But if you don't care about that, then it is, I think, a day.
Yeah.
No, that is a lot of work. Usually and this might be too deep of a conversation for this workshop. Organizers, please stop.
Yeah, I wanted to propose to move to Slack in case for a chat, or we will have 20 minutes after to discuss. There is just a lot of presentations and a lot of people would like to show something. So maybe we will move to next speaker then.
Thank you for wrangling the group.
Sorry.
That's perfect. It's your job.
And so next one will be Vincenzo Padulano and Enrique Teodor Saavedra from CERN, and they will talk about Dask backend for distributed air data frame.
Hi, yeah, thanks, Oksana. Let me share my screen, see if you can all see that. So you should be able to see the screen, right?
Yep.
Okay, let me just get rid of the Zoom interface here. All right, cool. So I'll just start with a quick outline of this presentation about Dask and root our data frame. So yeah, I'll talk about root and I'll talk about our data frame. And we'll see how we implemented a way to distribute our data frame operations on a Dask cluster. I'll also have a small demo for you to see what I mean when I'm talking about our data frame and Dask together. And we'll finalize the presentation with some numbers, some performance tests that we ran. So in a nutshell, Root is an open source software framework that does mainly data analysis, processing, and visualization. It is written in C++, but it provides Python interface, a Python API. And it's a widely adopted framework in high energy physics, but we've seen it used also in other scientific fields and in industry. So in Root, we have this R data frame interface, which is something like a Pandas data frame or a Spark data frame. So it's a declarative interface for data analysis. You can have multiple data sources with different formats coming in, and you can define a set of operations that should be run on the data set, like filtering the unimportant events, creating new columns, and finally retrieving whatever result you need for your analysis. And all of this happens in a lazy way. So the computations start only when you actually access the final results for the analysis. The idea with R data frame is to have a single entry point that can fit in most high energy physics use cases, and at the same time provide the best performance possible. So to that, very recently, we introduced a distributed module that takes the R data frame computation graph and distributes that to a set of computing resources. Now, we are trying to make this as agnostic as possible with respect to the backend scheduler used for the distribution of the computations. In fact, we already have a function and implementation with Spark, but today we'll focus, and I will show you how we did create a backend for our data frame with Dask as well. So the idea for the user is to have the same code that they created to run our data frame on their laptop, and just be able to use that code and run the computations on a Dask cluster, for example. But behind the scenes, what is happening is that this distributed application will read the original dataset of the analysis and create small ranges of entries. And the list of these ranges that you see in this picture here will be sent to the cluster of distributed resources. Then for each of this range of entries, we will create a mapper task. And the mapper task will be responsible for retrieving from the dataset only those entries that are needed inside the task and nothing more. So any mapper will not read the whole dataset, that is. Whenever the partial results are coming in from the mappers, they will be reduced still on the cluster of resources, and just the final result will be sent back to the user in a transparent way. So how does all of this translate to Dask? So what we did is that we already had the implementation for the mapper and the reuser functions in this distributed R data frame module, and we wrapped them in the Dask delayed decorator. So with this, we're able to create our own computation graph in Dask, leveraging the tasks that we create within our data frame. And in code, that looks something like what you see on the left side of this slide. So other than wrapping the mappers and reducers in delayed objects, we create here the computation graph by issuing one mapper per each range of the list of ranges that I mentioned previously. And then the mappers will iteratively get reduced until there is only one result left, and that result will be sent to the user. And you can see on the right here that looks like a map reduce pattern in the end. And that is also very similar to what we have in the implementation of the Spark backend. I will briefly talk about that later. But now let me just mention one thing, which is quite important in this case. With our data frame and with distributed R data frame, we leverage the Python interface that is available in Root. And that with that interface, we can also interact with Dask. But under the hood, in reality, we are running Root C++ computations. So this would happen even without Dask. This happens already in a laptop that runs a Root application. But this is also especially important because this means that we will run C++ in the Dask workers. And since we have seen that with Dask, you can run also in a multi-threaded configuration in the cluster, in the workers, we had to make sure that we were releasing the GIL, for example, and enabling the thread safety on the root side in order to avoid contention on the workers themselves. So finally, before going to the demo, some of the differences that we saw were for the development of the Dask backend with respect to the Spark backend. Well, clearly we have a different API. Of course, they are two different tools. So with Dask, we use the delayed interface. As with Spark, we use the native map and tree reduce API. But other than that, the computation graph itself looks quite the same. And yeah, we created in this way to be, let's say, more similar, to have something that we already know, that we already knew. One other difference, which is just how the two tools work, is that with Spark, all the mappers get executed in a first stage, and then whenever all the mappers are finished, they will get reduced in a separate stage. Whereas we saw that with Dask, this is not the case, because whenever at least two mappers are finished their execution, they can just get reduced. Also, while other mappers still have to finish. So that's simply one of the differences that we found. So now let me jump to a small demo that I have. On the slides, I also left the link to the GitHub notebook. You will find it later. We'll find a way to share the slides. But now let me jump to the actual notebook here. And this notebook is in a Jupyter interface that we have at CERN. It's a web interface for data analysis that's called Swan. In particular, in this notebook, I will analyze a data set with our data frame. And this data set contains roughly 60 million events that were recorded in 2012 by the CMS experiment at CERN. So the first step for this demo here is to import the root module. And this is just the Python interface to root. But as I said, the main functionality will still stay on the C++ side. Then, okay, this is just simply a representation of what I described before. The computation graph of our data frame can be executed locally on a laptop. And today we'll see how this can be transparently sent to a Dask cluster. And in fact, let's just create a connection to that cluster. In this cell, we are using the client interface to connect to this cluster, which we created specifically for the purpose of this demo. So it's a virtual machine cluster at CERN. You can see there's a link to the dashboard that we will have a look at later. And this cluster only, for now, it has 16 workers with 1 core each. All right, so now let's go to actually create the dataset with our data frame. Or connect to the dataset. This dataset in particular is stored at the remote storage system at CERN that is called EOS. So with this dataset, what we need to do is that we need to create an R data frame object that is also aware of how to send the computations to the Dask cluster. And in order to do that, we have to point, as you see in this cell here, we have to point the R data frame call to the specific R data frame object defined inside the distributed.dask submodule in root. And okay, so once we did that, here is the actual R data frame constructor. Let's see the arguments very quickly. The first one is the name of the dataset, and the second one is the location of the dataset on the remote storage. But then we have two optional parameters, which are quite important for the connection to Dask. In fact, the first optional parameter is called n-partitions and translates roughly to the number of mapper tasks that the Dask cluster will execute. And then we just have the connection to the Dask cluster that we created previously. Now, I want to stress out one thing here. If we removed these two optional parameters, this would look just the same as a R data frame constructor that runs on a laptop. And what you will see below that, below this cell, all the API, all the function calls, everything looks just the same as an R data frame analysis that runs on a laptop. So this is what I meant when I said that we are trying to be as transparent as possible for the users, because the only thing that you need to change to go from your laptop to a Dask cluster are these two optional parameters to the RData frame constructor. So the actual analysis itself, let me create the RData frame here. The analysis itself is as follows. We need to filter the unimportant events from the dataset, and then we will compute a new column. So we will create a new column in the dataset that is called dimuon mass. And what you see here as the second argument to this function is a Python string, but in fact, this will be translated to a C++ call. Actually, it's a function defined in the root framework that will compute the invariant mass of the particles in the dataset. And with that column defined, we can now create an histogram object out of the column that will be the actual result of our demo. And in fact, what is happening here is that so far we didn't trigger any computation at all. If you saw, the cells were just executing very quickly. The actual computations will be triggered whenever we try to access the result of this histogram. And in particular, this happens in this cell. So if I execute it, you'll see that it's starting the execution, and we could go to the Dask dashboard. You see that we already have the map reduce pattern that I previously mentioned. The first line will be made of all the mappers, and all other vertical lines are made of the reducers that are waiting the mappers to finish. This is just the status dashboard of Dask. So if you have used Dask before, I think you already know about this. You can go here, take a closer look at the mapper tasks that have just run. So the analysis actually is just finished. We can go back to the notebook. And now what has happened is that we computed the histogram distributedly, but the histogram was sent back to the notebook. So what we can do is that we can just plot it in this cell. And you can see that we get the result of the analysis in our Jupyter Notebook session. All right, so that was it for the demo. Let me go back to the slides. And I just need to finish the slides with some tests that we ran. So the test here is the same analysis that I just showed you in the notebook, but let's say a bit with some increased values. In particular, the cluster was increased from 16 cores to 48 cores. And we also configured the workers to use multiprocessing rather than multi-threading, because we saw with our tests that for some reason that we are still not sure, but multiprocessing configuration was a bit faster than multi-threading configuration. And then the dataset itself, we took the same analysis as said, and the same dataset, but we replicated the dataset 100 folds. So this means that we will actually read and process 200 gigabytes of data in this case. And this is the result of what we have done. On the left side, you have the runtime of this application with increasing number of cores up to 48. And on the right side, you have the speed up of the application. Again, the speed up in this case is with respect to the baseline of 4 cores, but it's still up to 48. And you see the comparison with the linear speed up with which we are quite close. This result, as you see here, is quite similar to the result that we got when using the Spark cluster instead of the Dask cluster. So that's also quite promising for us. So in conclusion, our data frame is Root's declarative interface for data analysis. We have recently integrated it with support for distributed computations. In particular, today we saw also the implementation of a Dask backend for distributed R data frame. And we just wanted to finish the discussion with some feedback from us. As I just mentioned, we saw better performance when using multiprocesses rather than multi-threading with the Dask workers. And another thing that we noticed is that even when we actually were sure we were releasing the GIL, sometimes we still saw these kind of warnings in the worker logs of Dask that were telling us that the workers were unresponsive for some time. But still, we didn't see any errors or any timeouts. So we're not quite sure if this is something that we should be stressed about or not. With that said, yeah, that's it for me. So thank you for your attention. And if you have any questions or comments, I would be glad to hear them.
Thank you very much, Vincenzo. It's nice to see Root, making use of Dask. Yeah, so I'm just curious if there are any questions to Vincenzo. I have some of my own, but Doug, you're unmuting. Do you have a question?
Yeah, I wrote it in the chat, but it basically showed the plot of the scaling and how you're beginning to fall off at the linear scaling. Do you have any idea what the reasons could be?
So for us, Dask is a very recent effort. So with Spark, we have had some issues that we found along the way during the development, and some of them were solved. We are aware of some issues that are actually independent on the backend, but have to do with some implementation, internal implementation in distributed R data frame. But what we are still missing is, for example, what are the differences between Spark and Dask? So what we know is that we are creating roughly the same computation graph, but we still can't understand why with Dask there is, for now at least, slightly worse scaling than with the Spark. So some things are known, other things are still unknown.
So maybe I can ask a question. So I was curious. So in the sense, so you started off the talk with, I mean, being our data frame being kind of a declarative interface to columnar analysis, and so I think kind of if you start out, yeah, with the integration, like if you want to do like the Dask and Spark, I mean, I can definitely understand that the easiest thing is to keep a lot of the logic kind of inside of root, but I was wondering, we had this discussion about kind of extending like the native Dask, data types and stuff like that, whether or not there would be kind of like a way to translate kind of the DAG that you're building up kind of inside of the R data frame grammar, so to say, and, convert that into kind of like an actual DAG in Dask, or whether you see just for kind of uniformity that you want to support Dask and Spark and all these things kind of at the same level, on the same footing, that you'll kind of keep on this level of integration.
Yeah, so I think it's the second option, at least with this effort in particular. The main reason that I would say for that is what you see in this slide, is that we are trying to provide a uniform behavior that is independent on the back end. So what we are doing here is that we are splitting the work depending on the data set and on the ranges of entries, and not on the tasks that make up the R data frame computation graph. So we'd like to keep the R data frame computation graph as a single unique event loop that happens on the C++ side, and then split the computations along the data set itself.
Yeah, yeah, I mean, I can understand that. So I think to some extent, I mean, there's some overlap kind of what our data frame kind of used to do. I mean, these types of splitting of columns into chunks, of course, is something that in Dask array, Dask is also doing. So I think you need to find some way where to delineate kind of the responsibilities.
If I may add something here, it's also important that we are using both Dask, Dask backend and Spark. It's the same thing. We're using both of them as just schedulers to create our tasks and to schedule our tasks. But they don't really know about our data. So all the data is read with the root IO libraries and is read remotely, right? And we want to keep that. Like, we want to manage our data and read it with our libraries in C++. So that's perhaps because we have our own format, the root format, and we have our own libraries to read it, which know how to read it efficiently.
I mean, for example,
so I don't know how that would integrate with Dask.
Yeah,
how that
would follow the mechanism of other binary formats that Dask reads in.
So I think we can move this discussion to the Slack.
Yes.
Because we're a bit running a bit late. So thanks again, Vincenzo, for this talk. And yeah, so I need to actually check who's next. This is Wei.
Yeah. I think, we're moving now more to infrastructure level. So we started with our software development. And now, Wei, please, your stage, how you use Dask. The talk will be about Dask in Slack National Laboratory.
Sure, let me share the slide. Wait a second. All right, it's not quite about, I'm going to switch the topic from software to the infrastructure and how we facilitate the use of Dask in the US Atlas analysis facilities. Not much completely about Slack, because Slack has many components which are not necessarily high energy physics. So, oops, how do I, okay. So we are currently, this Atlas user analysis facility is what is used to facilitate Atlas users on the LHC experiment. So right now the experiment is undergoing some upgrade, but after the upgrade, we were going to run it at a much higher level of luminosity, and that will translate into a much higher level of data rate. So in doing that and in facing with the flat budget, we're going to have a huge challenge in processing our data. That is including both the official data production pipeline and also in terms of after that the user analysis. So one of the things we are trying to look at is to explore the whole experiment is try to explore using Python ecosystems, which is a core part of the industry data science to address this data volume challenge. And I believe that we are well positioned to do that because not only we have all these developers, and we just heard the 2 talks before us developing the software, but also we have a very young user base that are willing to learn. And this pie chart show you that 3/4 of our users are actually graduate students and postdocs. So they are very eager to learn new things. So in the US, we have the US Atlas, which is the US participation of this experiment, found 3 user analysis facilities. Their missions is not to participate in the data production pipeline, but to facilitate users analyzing the data produced by this data production pipeline. So one of the things that we are trying to help is to show users how to use Dask in our facilities, among many other things. So these 3 facilities located at Brookhaven National Laboratory, Slack National Accelerator Laboratory, and coming soon will be University of Chicago as well. So I use the Slack's environment as an example. You see that it's a relatively standard HPC setup with a Slurm environment, and the Jupyter instance run as Slurm jobs, and Dask will also run as Slurm jobs. So we believe that the analysis facility has a role to help our users to use Dask. Some of these are very obvious. For example, if you, let's say you are at Slack, you use Slurm, and we need to provide them some of the technical details of how to use, how to configure the code to use the Slurm environment. For example, what account you use, sometimes that's actually a tricky part. And if at some point they want to use Dask dashboard, and how are they going to do that? Which host they should be able to connect to for the forward, the port, etc. These are very common, easy to understand thing. In the meantime, in the facility, we also provide some kind of a common integrated Python environment for them. For example, some of the users want to use Dask. We package Dask in our environment, but along with that also includes root, we include uproot and include CUDA libraries so that they can use this library along with Dask. We package them through, in most cases, through the combination of Conda and PIP. But in some cases, for example, at Brookhaven, we also use a virtual environment. And because of all these packages consist of millions of small files, we sort of try to speed up the performance by putting some of the common things in Singularity, some of the environment in a Singularity container, so that we can help them speed up the load of those libraries. And when doing so, we're sort of trying to make sure that this environment are expandable by the users themselves, because we know that no matter how many things we put it in, there are always something that the user want that we didn't provide. So we are also trying to help users to access data, which is actually an important part. Without data, they can't really do much. So this includes helping them to access data through remote access using protocols like HTTP or root, or help them copy the data to a shared file system, or in some cases also even copy to the local bash nodes scratch space. And obviously, we also provide periodical provide training documentations and periodical trainings. From my observation, our users, not those advanced users who are developing software, but the users actually doing the physics analysis are just start using Dask. So they're exploring Dask in many creative ways. There are also a lot of large or small efforts in embedding Dask in various physics analysis workflows. When I say these workflows, means that if somebody have an idea of what kind of physics they want to look at, they actually most of them actually needs to go through several steps to eventually get a physics result. And in some steps, they will need to analyze the data, obviously, and Dask is something that they try to embed into that analysis. Some of them are very complicated, some of them could be very simple. Also, from what I learned, that most of the Dask users use Dask for data processing, not for machine learning. I know that machine learning is a hot topic, but in our case, what we see in our facilities is that they are using mostly for data processing. And as previous speakers all mentioned, we have a root data format, which is HEP developed the data format, and we use root format to primarily store two kinds of data for users to analyze. One is DAOD, which require ATAS software framework to read. And the other is a flat untuples, which does not require the software to read. But regardless, both of them require root, either root library or uproot to read them. So in the flat untuples, we have some official ATAS data products like Face or Face Lite, but we also have user-created condensed data formats that they use for repeated final stage analysis. And these data files, whether it's user data files or it's Face or Face Lite or DAODs, they are independent files. So each file is only important in the sense that they contribute to the overall statistics, to improve the statistics. So this makes HEP computing is as an embarrassingly parallel. I probably don't like the word embarrassing because there is nothing really embarrassing, but it's naturally parallel. And Dask is a very good fit for this kind of tasks. But as I said, we are sort of focusing on the root data format, but there are also other R&D activities are using other data formats like Arcade, HDF5, and we just talk about other things. But those are R&D activities. Right now, the vast majority of our data is in root format, so we'll be focusing on the root format. So how do the users use Dask for data processing? Every data processor starts by reading data. So the format have a big impact on how they start using Dask. And there are multiple ways you can use uproot and upload array to do that. You can use roots, data frames. The two previous speakers talked about these topics, but there are also users who do something. We actually find that several users who do something in a much more simple way. They just use root pandas or root NumPy to do that. I don't know. That's probably very easy to get started, but I don't know what kind of limitation of these packages they will be imposed. I also heard that the users use Dask in a way that they sort of write their entire analysis first for an individual data file, and then probably use PyRule or something like that. Then they map the entire analysis as a Dask task, use Dask just for scheduling, and assign an input file to this task. And then naturally they parallelize all these things, and at the end they get all the results together. So this is another way that we heard that they use Dask. So as a facility, since we have sort of GPU resources, we're also trying to introduce users to use the GPUs. So we show them examples of how to use CoolPy, CoolDF, and Dask CoolDAV, things like that. But as far as I know, our users are far more CPU ready than GPU ready. I haven't heard of anybody coming back and ask me how to do that, how to use CoolPy or CoolDF, or complain about that. So in the future, I believe that we will need to use Dask probably in the US Atlas analysis facilities for many other things. We are closely following the R&D efforts of Iris HEP project. And I should actually also say that Atlas internally has a data modeling and analysis modeling, and we're also looking at what they are doing. So basically, some of these efforts, including Iris HEP and others, is to try to excuse me, modernize the user analysis by adopting the industry data science tools. And there are many, I show here there are many components of many kinds of things that they are trying to do. Some of them are very obvious that will use Dask, but others are sort of indirect. For example, a big piece of this is the ServiceX, which they will want to convert root data format data to columnar data format. So if we are going to do this, this will likely significantly boost the Dask adoptions, because now users analysis will not start from the root format. So they will have other options and probably more easily engage in using industry's ways of doing analysis. We are also exploring the cloud, and the US Atlas has set up the R&D project to explore cloud, is in particular with Google Cloud. And I'm not going to go to the pros and cons of using cloud, but I would say that the cloud provides many of the things, software or hardware, that we don't have in our facilities. So that's something when our users need, they can go into. And some of these will probably also help our users to use Dask. So because of that, Dask is a focusing topic in our R&D when we talk about this cloud computing. And along that, we also have some ideas or discussions, but not really actions about extending Dask to use the Panda as the backend. Panda is Atlas' worldwide workflow management system, and constantly handling about 500,000 job slots for Atlas data production pipeline all the time. So we sort of trying to use that as a backend to see whether we can use Dask to submit jobs to Panda, and that's probably just R&D make sure to see whether there is any use case. But regardless of all this, our biggest thing one of the big things that we need to decide, not necessarily say for good or bad, but need to decide is the data format, and we need to understand whether that's what are we going to do. So in summary, as part of the idea of turning into industry data science tools for user analysis, there is a lot of interest in Atlas computing about Dask. Also, there are lots of ideas showing up. Some of them are new, some of them are more mature than others. And we're sort of just trying to understand that when users have this question and help them. Data format is a question that we wait to see whether our current root-based format is efficient enough. Everybody hopes that it's going to be efficient enough so that we don't have to do data convert, but maybe maybe we do have, nobody knows. But regardless, this will have an impact of how our users will use Dask. So at the facility level, we are center place for users to learn and test, learn the Dask and test this Dask code in large scales. We provide software and hardware resources, we provide technical support, and in some cases, we even have to give users a little bit of guidance of how to use that. Thank you.
Okay,
Thanks a
thank you,
lot.
Wei. I see Doug has a question. Yeah, we're still running a bit late, so maybe we just have a few questions and then move on. Doug, go ahead.
How much of this design implies what reading over the wire within the data center, as opposed to copy to scratch?
Well, we don't really dictate that part. In fact, if you really, in some cases, if we really want to discourage users who to do read over the wire, over the wide area network because of the efficiency. There is nothing you can.
I'm not talking about wide area. I'm talking about LAN, read over the wire in the LAN.
Oh yeah. So in that case, almost all of them, even when you use a shared file system, it's actually using sort of that sort of things, right? Unless you copy to scratch. So there is no way you can put all the data on a local scratch disk and analyze them on a single machine.
I have maybe one quick question. So in terms of, so we've seen also in VCHAP Coffee Casa in terms of an else facility to deploy maybe at different facilities. So do you, is this like your setup that you have at Slack, something that is specific to Slack, or is it kind of something that could be deployed at multiple institutions and then federated among themselves?
If you look at it, no, the answer is we actually deploy a similar environment with Brookhaven, and so the environment is sort of similar. My understanding is that there are sort of a deployment model that you are looking at, like using Kubernetes to deploy the software and the environment. This has to, there is nothing against it, but this has to fit into the site's security policies and also what site's most investment is. For example, we at both Slack and Brookhaven, we already invest a lot of resources in the batch systems, and if your startup is willing to fund us to deploy another Kubernetes cluster, we'll be happy to do that. But unless that happens, really we don't have the resource to do it.
Okay, thank you. I think we need to move on. If there are any other questions, please use the Slack, and maybe we have some time for discussion later on. So the next talk is, let me check, is Maria on Coffee Casa, actually.
Maria and Carol, yeah. The experience now from USCMS Fermilab and from UNM.
So I'll trust you can hear me. We're going to switch off speakers in the middle of this, and so I hope that's not terribly awkward. Our talk today, and it's presented by a couple of us, is less about Dask and more about the seismic shift in high energy particle physics and data analysis. And as a quick hint at why we're doing these things, the LHC experiment CMS, which is what I'm part of, generates about 10 petabytes of data yearly. But no single analyst is going to want to do an analysis over all 10 petabytes, but they're still going to want to analyze over hundreds of terabytes, which is not an insignificant amount of data. The problem is the data model, the ability to analyze this data was all envisioned and imagined about a quarter of a century ago. And so what was possible 25 years ago and what they presumed might be possible in 25 years starts to miss the mark a little bit. And so even though things have changed, the data model is designed in quite a different landscape. In order to do distributed computing, what they imagined was the best way to distribute it was distributed over the globe. And so what was constructed was a global grid of computing resources. And here you can see the globe and all the ribbons going to sites. Those lines eventually terminate at sites like Fermilab in Nebraska. And terminating at Nebraska is where we enter into the fray, right? We at the Holland Computing Center here at Nebraska are one of the terminus points for the resources that participate in this world analysis grid, right? We've housed one of these CMS Tier 2 facilities since 2006. And some of the features, maybe it's bugs now of that resource is it features a high throughput batch queue. We have a large distributed file system, large being whatever you want to term it. In 2006, large meant 40 terabytes. Today, I have about 14 petabytes on the floor. So it's varied over the years. The way to access this resource is through the Open Science Grid's grid interfaces, which requires X509 based access controls. And there's almost no interactive interfaces. And when I say almost, if you have a friend of a friend, we do co-locate like a Tier 3 facility here, which would kind of sneak in the back door. But this represents what I would call an established resource for CMS. These are the types of resources that we put on the floor over the past 15 or 16 years to do the data analysis from CMS. The trouble is they're not designed well for a new data analysis paradigm. And so what we're trying to investigate here is how are the facilities reacting and changing to accommodate this new user approach to data analysis. So let's take a look at the current physicists' experience analyzing data at CMS. First of all, they log into a terminal like some sort of Neanderthal. They develop really intricate code. The code base for our analysis is about, it's close to 20 years old. Of course, they debug, they test, refine. They may run locally over a small sample, and it may not be so small if they have a pretty substantial local compute resource. That helps them do the refining and the debugging. So, 3 and 4 create an iterative loop. And when they're pretty happy with everything, then they submit their jobs out to the grid using their 509 proxy, and they scatter across the globe, and they wait, and they wait. And that waiting could be several hours, it could be a week. The unfortunate part is it's not really deterministic, right? They don't know how long they're going to have to wait. And sometimes most of it will work and some of it will not. And so you get failed jobs coming back and you're saying, well, what do I do with these? Do I throw them away? Do I try them, retry them? Is there a bad site that's hoovering up my jobs and making them reschedule until it gives up? What's going on? What this creates, I feel, is a frustrating computer experience. So how do we change that? There are several things that are going on, none of which I'm fueling. I think the community itself is fueling. First, we're moving away from terminals to Jupyter. I think that's a natural thing to move to something more comfortable. And I hear that's what all the kids is using today. So, we got the Jupyters coming online. As far as developing intricate code, we have some very energetic developers who are building something called Coffee, which I think, among other things, helps to abstract away from that intricate code and really encapsulate the complexity of the analysis in tools that the physicist really doesn't have to think too heavily about. So Coffee's on the way. Unfortunately, step 3, the debug, test, refine, I have not found a way to get away from that. If you find a physicist who can write bugless code, let me know, we'll hire him. And then the rest of it, we want to get rid of altogether. This run locally over small samples, the X509 certificate stuff, the waiting, and the fragility of the remote jobs. We want to get rid of that. And so we'd like to slide this over to running over the entire data set in near real time, right? And Coffee is going to allow us to do that if I could get it enough resources to bring to bear. What we'd like to have for physicists is we want them to get insight, not frustrated. And the unofficial model here at Holland is, reducing the time to science. We'd like these people doing science, not pulling their hair out, wondering why their jobs fail. Like I said, Jupyter, of course, I think the move to Jupyter and Python has been very natural. Even when I was a graduate student, Python was starting to rear its head as something that people should paying attention to. I, of course, chose Perl badly, but there we are. And coffee, I think, brings a lot of the modern day big data analysis tools to the HEP community, SciPy, NumPy, and they're all tailored to interface with, HP data using uproot and RD data frames and these sorts of things, right? So where can Nebraska, a facility, add value? Where can we help out here? I bring up what I did a couple of years ago, just so that you get an idea of the sort of the things we're doing in the back end to facilitate this parallelization of a Jupyter notebook into a Condor resource. First thing I did is create a Dask scheduler. I created a Docker image with coffee and Dask worker code baked in, submitted that out to the schedule so that all the workers are waiting, calling back to the scheduler. And then I logged into my notebook, pointed at the scheduler, and ta-da, I was running jobs inside HT Condor. At that time, this required a lot of special access that I have because I'm an admin. A lot of tinkering with Condor settings. This is much better now. The Dask job queue libraries, which I think Matt Messi at Wisconsin has developed, makes a lot of this a lot easier to do, but it's still not something I want to release physicists onto because I think it still carries too much complexity. So along came this idea for Coffee Casa. The red circle represents our existing established resources, the stuff that we can't replace because we spent tens of millions of dollars on it. The blue circle represents what users are expecting to bring to the table. And so what Nebraska and Purdue and Fermilab and these other sites can do to help add to the ecosystem is create that connective tissue between the user face and the resource. Okay. We created something called Coffee Casa, and it needed some of the following connective tissue. We needed a Jupyter Hub instance. We needed a Dask scheduler for every user because Dask doesn't seem to be a very multi-user friendly thing. We wanted some immediate just-in-time resources, so we didn't necessarily want to wait for Condor to spin up everything. We wanted to make sure everything was secure, and we wanted to get rid of X509s. We did tokens and so forth. We wanted all the scaling to be transparent to the user. We wanted to make sure that there were multiple instances so that my incredibly bright developers could have things to play with and break while our testers tested things that are relatively stable. And we finally need this to have a pretty lightweight management footprint because I'm not getting more people to work on my resource. All right, so Holland basically brought a Kubernetes resource to the table. I brought a Jupyter Hub instance and married it to authenticating against the CERN CMS database. Along comes Oksana Shadura and Brian Bockelman, and they flesh out the meat and potatoes of the user's pod to get them some just-in-time resources, to get them a class which they can automatically send to Condor and get these things to scale naturally. Right now, of course, Coffee Casa is still undergoing a lot of development. We're bringing some more services on board, and the nice thing about using Kubernetes is it's pretty easy to onboard new services like ServiceX and Skyhook. These are things like data transport layers and data transport services and object stores that maybe we can do storage of intermittent objects as analysis progresses through the system. So a lot of stuff is still going on here at Nebraska, and I'll pass this off now to my colleague Maria. And I got to do that by stopping share.
Thanks. Yeah, so we don't have a huge ton of time, Maria. I don't know how many slides to have, but yeah, maybe we can go quickly. Thank you.
Okay, I'll make sure to go fast. So if you can go a little bit into the previous slide. Oh, okay. I'll just share my screen. All right. Can you guys see that all right?
Yep. Okay.
So kind of tying up into Carl's talk about Coffee Casa. He talked a little bit about the Nebraska Tier 2, and the case for Fermilab is similar. So you're going to see a lot of FNAL in this talk. So FNAL is short for Fermi National Accelerator Laboratory, which most of you know of. You might know as America's Particle Physics and Accelerator Laboratory. It's the home of the Tevatron, which was like the grandfather of the LHC. It's a tier 1 computing center for the CMS experiment. So we also offer batch computing resources as well as disk and tape storage. It is a national lab, and we host, we're a big CMS place, but we also host smaller or different experiments such as Dune, Nova, the Dark Energy Survey, etc. So that means we have a little bit more on our plate than just CMS. So the elastic analysis facility at Fermilab started a couple years ago. We just had a Rusty Spark cluster and a Rusty Dask cluster sitting there, and once in a while someone would send some analysis test jobs there. Another thing is that back when we started, this is a very new thing, so there was no computing policy at all around containers or container orchestration. So we had to kind of pave the way to basically make DOE and cybersecurity happy. We developed our own notebooks. These are just Jupyter notebooks with basic grid utilities. And from the beginning, there was a huge interest on being early Coffee Casa adopters. So there's an active collaboration right now with the Coffee Casa developers, with Oksana, to identify and patch any hard-coded or any leftovers from previous builds. So the preliminary results, the first thing that we're kind of proud of is that we were able to deploy Coffee Casa as a whole. So we took Carl's and Oksana's Docker images and threw them into our notebook catalog. And so suddenly all CMS users that are stationed at Fermilab or have Fermilab accounts can do Coffee Casa style analysis. We have an analytics hub web UI up and running where you some of our users, you just log in and you get a list of notebooks you have available to you. And then the Kubernetes provisioner will throw a pod out there for you and kind of show it back to you in the form of a Jupyter Lab environment. All our code is stored, built, and tested in our GitLab infrastructure. So we're trying to do everything in a kind of DevOpsy, SRE, consistent kind of way. We don't want to get bitten in the future with technical debt. Another thing that we developed is the capability of deploying custom entire farms of Condor workers with a single Kubernetes instantiate command. So what I'm actually doing right now is investigating how I can do this type of bursting of task workers. So when we have a high demand for extensive task analysis, we are able to contract the facility with contract the Condor workers and allow more resources for Dask, which is interesting for sure. This is a little bit of what we have right now. So there's our Jupyter instance. There will be some sort of column service in the future. We have Dask in here. We have a small area of the facility for Condor, and then we just recently deployed Service X, which is an Iris Hub effort. So some things to consider here is that we have the idea is to have a centralized Jupyter Hub deployment, but of course centralized means that we have to support multiple experiments, multiple users. Experiments have policies within their own organization, so we have to leverage all of that and try to offer a resource for everyone to kind of take advantage of it. We also are talking with our neutrino friends and see if we can do something similar to what Coffee does, which is a columnar analysis with their neutrino files or their neutrino analysis. Dune, for example, which is one of the experiments that's set for commissioning, it's exploring having Jupyter Hub as a submit door for the Condor pool. But this leaves us with a lot of questions regarding authentication, authorizations. We have a bunch of usernames. We have users registered in multiple experiments. So these are the main questions that we're actually trying to solve right now. I know this is a very texty slide, but basically I just wanted to share with you guys that we have the multi-tenancy problem at the analysis facility, and we are trying to solve it via Jupyter Hub and tools. So we are able to authenticate users with LDAP, but then authorization becomes a problem. We're trying to integrate Ferry, which for those of you who are not familiar with it, it's a centralized source of information for Fermilab experiments and users. And we're also taking into advantage the fact that the Jupyter Hub is highly configurable. You can put in a Python script, and if you write it right, Jupyter will do what you want. So we're taking advantage of that. And the last problem that we had is that we were able to run Coffee Casa, but the scalability of a single Jupyter Hub instance is questionable, especially if we have I don't know, 25 experiments, and just as I was testing, I found myself building and pushing 16 different notebooks at a time, which is not it's not a good operative practice, I would say. So yes, we have a greater audience and we can do a great thing, but it also has a price. Building Docker, I'm sure everyone has run into this. It's just gonna murder your disk if you're not careful. If you have to build notebooks over and over again because we're in testing, it will just open the door for a lot of errors and a lot of setbacks. So the way we're trying to solve this is by using Binder Hub or leveraging Binder Hub for what we need. So basically, Binder Hub will build Docker images out of Git repositories and then push them to a Docker registry so that Jupyter Hub can launch user servers based on these images. I gotta say, it doesn't only build Docker images, but it could also provision IPNYB, which are notebooks, pure notebook, Jupyter notebook code. And then having Binder helps us with automation, relieves our operational burden. It's a centralized source, so we can the lab we have control for which notebooks we can offer, but it also opens up the possibility to in the future to let users run their own notebooks within Kubernetes without major hassle. So we think this is a great tool. So basically, the concept is you have a GitLab repository or a GitHub repository with a notebook you want, and you have a user. So your user will go to the Binder web interface. It's going to log in. So right now we have LDAP authentication here. And our Binder Hub is connected to our Jupyter Hub, not only through an API token for launching notebooks, but it's also our Jupyter Hub is our OAuth provider for Binder Hub. So when a user logins into Binder, the login call actually goes back to Jupyter Hub. If the user is authorized, then they will be able to retrieve their repository or our own repository with different notebooks. It's gonna trigger a build through the repo to Docker pod, and then it's gonna launch a Jupyter notebook in Kubernetes, and then it will give the user the notebook that they asked for which was in principle just some piece of code in GitHub. So the ingredients, I'm just going to go through this real quick. If your repository looks like this, which is what it currently looks like for me, where you have a bunch of different Jupyter notebooks, you have all sorts of combinations of software, then this was very useful for us. So number one ingredient, Git repository with multiple notebooks, you got it. The second ingredient is the Jupyter Hub on Kubernetes, already set up for deploy for spawning Kubernetes notebooks. Check, you got it. Number three, Kubernetes. You need a place where you can burst and get the provision the notebooks and get them back to the user. And then the procedure I put in here that it's just a single command. I use Helm to install this. I know there are plans to get Coffee into Helm, and we're also super excited on testing this. But the procedure is just one command, and then you will get all the infrastructure that I just mentioned. So just to kind of close this up, this is what we have right now. So we have multiple centrally curated notebooks. We will make them available for users on demand. They will be built at runtime from Git commits or changes. So this is also good because we have to be up to date with security patches and such requirements from cybersecurity. It's not only experiment oriented, but we also are looking into analysis type oriented options. So instead of having the CMS Coffee Dask notebook, we would have a Dask notebook where we can get more of our neutrino or astrophysics users to come in and use Dask and experiment with Dask and other data science platforms. We have some GPUs that are coming in where we are going to be able to offer them to users, or at least a portion of them for their analysis. The largest current effort is being done on migrating to an OKD4 instance. For those of you who are not familiar with OKD, it's just the Red Hat implementation of vanilla Kubernetes. The migration takes time, but we're hoping to be at a pretty stable place soon. And then finally, the collaboration with Coffee Casa and RSHAP has been key. Thank you to Oksana, Nick, Lindsay Gray, Bird, everyone. We look forward to more exciting things to come. And that's it from me. Do you guys have any question for me or Carl?
I think we will actually, because we are super behind on the schedule, and Maria, it was amazing talk. I will get in touch with you later because I got a lot of feedback from your presentation. It's amazing. So let's move to Ricardo, and I think then we can have some generic discussion.
Okay, thank you, everyone.
Cool.
Yeah,
can you hear me?
Yeah, Ricardo, we can hear you.
Awesome. And you can see my screen, hopefully.
Yeah.
Okay. So thank you for the invitation. And if there's an issue with the connection, I'm just saying that I'm in a place where the connection is not very good. So hopefully this goes through. I'll present quickly some of the experiments that I've done with Dask at CERN. It was mostly the motivation was mostly to take a framework that was able to scale out pretty easily and check from the infrastructure side what was required. I work mostly on the infrastructure for CERN IT, so that's where my interest comes from. Of course, once you start using it, you get other interested as well. But basically, the main goal is to look at how the infrastructure would look like in these days if we wanted to support multiple workloads in one single or a couple of centralized clusters where we can deploy many tools. So I put here some examples. So we already talked about a lot about Jupyter Hub, also Binder. I'll mention a bit about that. Of course, Dask. Other tools like Kubeflow, and the goal is really to consolidate the usage of resources, and especially the resources that are scarce, like GPUs, so that was the goal, and also then to be able to scale out and to have an easy way to scale out to public cloud resources. And the goal there is to explore like the scarce resources that we have, like GPUs, get access to more on demand, resources that we'll never probably have on premises, like TPUs or IPUs, and other type of resources that might come up. So at CERN, we have a large cluster, a large data center with like tens of thousands, hundreds of thousands of CPU cores, and then but GPUs were still on the tens or just over 100 GPUs available. So we started looking, and we already heard in the previous talks that one of the nice entry points these days is to have some sort of Jupyter hub. We saw also Swan at CERN, which is also backed by Jupyter hub. So in this case, the integration with Dask, we deployed a test environment with Jupyter hub, where you could specify a custom image or a set of curated environments. In this case, I highlight the Dask one. This is an old version, but it's a screenshot from a long time ago. Then you can specify the profile you want for your notebook. And this will basically launch a Jupyter environment that has all the bits that you require to use Dask, and I'll mention a bit more after. But also we heard that one key thing was to manage these environments. So there are a couple of solutions. So if you use Swan at CERN, you have a base image, and then all the rest comes from CVMFS. There was interest from some users to have a way to define their own custom environments, and the tool called Binder that was just mentioned earlier by Maria. So we deployed that at CERN as well as a test environment, and this allows users to just define their environments, and this can be, for example, Dask. So this is actually our Dask environment is just a Binder repo that you can launch in this service. The whole installation is Kubernetes based and launched by Helm, as mentioned also in the previous talk, a similar deployment. There is a user persistent storage for each notebook, and then we use the CERN SSO OAuth 2 tokens to also access other services that are available at CERN from inside the notebook or from the jobs that run in the cluster, in this case, the Dask workers. So each notebook runs as a container, and I mentioned the rest. So the only other part I would mention is this part, Binder part. So allows really a nice way to define your custom environments, and not only that, not only for the notebooks, but also for the workers that you're spawning for the task workers, as they are launched also as containers in the Kubernetes cluster. So because notebooks have limited resources, then we need a nice way to scale out computation when you need more. So you might have a notebook that it has maybe a GPU or a couple of GPUs or a few CPUs, but you want to scale out to tens or hundreds. So there is the thing I started to look at was this Dask Jupyter extension. I found it really like a nice way to integrate into the Jupyter environment, and to use Dask Kubernetes. That was the first way that we tried to use Dask in this cluster. It basically means that the Dask workers will run in the same cluster the notebooks are running. The users can specify the number of workers, and there is also the auto-scaling feature from the library. By default, as I mentioned, this will run in the same cluster as the notebooks are running, but actually in a different node group or pool. Depending on the resources you ask, you might end up in a different node group, meaning a different set of nodes in the same cluster, maybe GPU nodes, if your notebook didn't have GPUs. One important thing is that this cluster is able to auto-scale, so it will grow and shrink based on the demand at the given moment. So one cool thing that I've been working a lot with is to have additional clusters configured in the same environment to be able to scale out to public clouds. We already have a couple of prototypes also for other services, but for Dask, the way this is integrated is quite interesting, and I'll mention it in a bit. There is work from US Atlas also to integrate, instead of doing Dask Kubernetes, just to use a gateway in the middle, and this is something that definitely we need. So we started looking together at this. So hopefully I can play this. So this is just a quick video where you see that there's this Dask extension in the Jupyter Lab environment. This should look pretty familiar. And once you go to it, you see the clusters that you have configured. So in this case, it's only the local cluster, the same cluster where the notebooks are running. What we have in other setups is that you have the additional clusters that might be on premises or they might be in the public cloud. And this allows you to have a really nice way, for example, if you have access to additional clusters, just to scale out your computation to public clouds. So the way this is defined is very similar. Then you can just choose a cluster by just dragging and dropping. The configuration is done. And in this case, we are doing some basic computation. You can see the dashboards are also very nicely integrated into the extension. So you get like this really cool Jupyter Lab environment where everything is centralized. So this is like the ultimate goal. This was the look and feel that I thought would be useful for end users, but then the backend infrastructure needs to play along. So the use cases that we have, just recapping, is the cluster that runs on Kubernetes, and then few nodes that run the notebooks, again, auto-scaling and possibility to use GPUs, and then you can delegate to scale out the computation, you can delegate to Dask, and then this will run on a same cluster or on a different cluster. If it is a different cluster, so what we've been playing with, we have a project to experiment with scaling out to public clouds. And in this case, we have a bunch of clusters deployed across these three main public cloud providers, so GCP, AWS, and Azure. We've been mostly focusing on GCP. You can see also that we can deploy in multiple regions. And then the main goal is to target here the GPUs, because this is where the resources are scarce on premises. But you can think that if you want to scale out computation and you need CPUs and that are not available currently on premises, this is also a very good use case. We also have a couple of tests with TPUs, which are quite interesting. I think that could also play a role there. I think that's it for this part. So a couple of points that are important. So I will raise again the GPU integration. So at CERN, we have a few V100s that are mostly used for machine learning and for model training, or a couple of use cases that really can benefit from double precision performance. But we really don't have a lot of those. So centralizing them and being able to just allocate them on demand is quite important. And then we have quite a bit more T4s, which get single precision performance, but not very good at double precision. They are used for inference in a machine learning, but they can also be used for general GPU computation. And then we started offering virtual GPUs recently. This is in the form of GPU sharing. It's not really this new physical partitioning of GPUs that multi-instance GPUs from NVIDIA offer. And basically the way we do the sharing is 1 T4 corresponds to 4 virtual GPUs. This is quite important for things like notebooks, because we can suddenly have a lot more capacity. But even for computation, if you end up in because it's time sharing, if the GPU is not loaded with 4 instances at a time, you actually can get some decent performance there as well. And then where the big potential is in public cloud resources. So we've done tests with a couple of hundred GPUs for a single workload, but we actually have access to several hundreds of GPUs. And basically these are extremely cost effective if you use them in this way that you auto scale. Because you just pay for what you actually use. So that's quite interesting. The other thing that is quite interesting is that we get very early access to new GPUs. So an example is the new A100s from NVIDIA that are already available in a couple of public clouds. So we started playing with that, also with multi-instance GPUs. So one interesting thing is that these A100s have this feature, and I'll show here, which is they are extremely high performance, and for things like anything tensor related. So machine learning is quite good, but also for general GPU computation. But one really cool feature is that you can divide a single GPU into multiple physical partitions. So in this case, for example, you could divide in seven different physical partitions, which would allow you to really have physical isolation of the workloads in the same card, which is not possible currently with these virtual GPUs, which is just GPU sharing. And the memory is shared, so the performance can be pretty bad. You can also partition in different ways. Instead of having 7 times, you can have two slices or 3 slices or a single slice. One really important thing that we want to test that we did not test yet with Dask here is that because we use Kubernetes, we need to be able to schedule the resources or the workloads to these specific partitions, and the NVIDIA driver or plugin for Kubernetes already supports this. So traditionally, you would just say NVIDIA.com GPU1 to get a GPU in Kubernetes, and this is what then Dask Kubernetes or whatever the Dask gateway that you might be using would use for the scheduling. But actually with MIG, you can specify the partition and the amount of memory that you want to use. These are not so flexible as you would expect, but this is how you pass it. So we need to validate that this is possible for Dask as well, and we will use this for the prototype deployment we have with the public cloud endpoints. One thing that comes out of this is that because we were mentioning auto-scaling being very important, and specifically when you're using public cloud, you really need to enable this so that you only pay when you're actually using the resources. What this means is that very often the workloads will run in a brand new node, which means that whatever Docker images you would maybe expect to be cached will not be there. They will be just pulled before the job starts if they are pretty large. And in HEP, you have a couple of examples where images are extremely large. It will take a while for the job to start. And this is basically time lost that you might be paying for the resources. So in the case of curated images, we could consider just preloading them. And for everything that is in CVMFS, this you could just load the rest from CVMFS. But actually, for custom environments where you're building the image using Binder, for example, there would be some delay for the image to be pulled, depending on the size of the image, of course. So there's a nice new format called STAR-GZ, which is aiming to do this, to target this, and to offer a way to start a container really fast and just trust that the contents of the image that are required at runtime will just be pulled as the workload is being run. So other improvements that we are looking at is also, again, in the Kubernetes area. One thing that is also quite important for things like Dask is that you want to support things like gang scheduling so that you can deploy a lot of workers in one go and make sure that you launch them all at the same time. There are some workloads where you might want this. When you get to the slot, you want to schedule them together so that the computation can go if there are some dependencies between them. Things like queues so that you can apply priorities as well, and also fair share, because we just heard before that there might be environments that are multi-tenant or you have multiple experiments running. So things like fair share for the scheduling is pretty important. The good news is that a lot of this is getting into the native Kubernetes scheduler already. If you need something like gang scheduling, you still need a project like Volcano or similar, but for queues or fair share, actually the required bits are already getting in. Kubernetes 121 already has part of them, and like Google is pushing pretty hard to get the whole thing there very soon. And that's all I have, and I'm very happy to answer any questions.
Thank you very much, Ricardo. So the connection held up pretty well, except for my own. I dropped out. But yeah, so I think it's yeah. So we're kind of seeing a pattern emerge, kind of also on the infrastructure side. So I think we can ask a few questions, kind of on both of these infrastructure talks from Carl, Maria, and Ricardo. So I see Doug has his hand raised. So we have something like 15 minutes for discussion, which actually won't be enough, I'm sure. So there seems to be a lot of interest. So maybe we should definitely try to organize a follow-up meeting, at least within the high energy physics community, to kind of get some action items going. But yeah, go ahead, Doug.
So how at CERN are you going to link in with the existing Condor ecosystem that exists, right? Because a large amount of your CPUs are living on in a Condor pool.
Yeah. So you mean in the context of Dask, is it?
Yeah, assuming that you're going to
So-
provide Dask, some of the Dask compute will be in that kind of pool, because there are a lot of
Right.
data centers that have one or two schedulers already. They're there already.
Yeah. So I think the goal there, honestly, because I've been really involved in Kubernetes, I've been focusing mostly on that backend, but I'm following very closely the work that Nebraska has been doing as well for integrating Dask with HT Condor. So I think whatever they're working on will be reused for sure. Like, I don't know of any specific activity integrating Dask with HT Condor at CERN. I know the upstream activities and I know the push from Nebraska. So I think there's a lot to share there.
Yeah, I just wanted to add a comment. So Ricardo, I was just following your work from the beginning, and let's say, yeah, you influenced it quite a lot. I think from certain point of view, there was the first, what I saw was a lot of tickets open to at least to open ports to have access at least from LX Plus. But I think the point is that when you will move to tokens, it should actually simplify life in the terms of, for example, your implementation. So you will not need to have any more X509 and
Yeah, I think that's a very good point. So that's one of the things we've done the OAuth integration. Basically, the first step was to get the auth tokens and the SSO integration running well with Kubernetes, because both this prototype that I showed here and Swan are moving to deploy things like notebooks on top of Kubernetes. There's also work to containerize LX Plus, and so the first step would be to have the credentials managed and refreshed inside the Kubernetes cluster. And then the second step is to make sure that all the services behind are accessible with OAuth tokens. So one that is already the case is EOS. So that's like step number one. It's a massive one because a lot of the storage is there, of course. We have requirements from people, and we started looking to integrate with Spark as well. And I know the Condor team is also looking into allowing access to Condor using OAuth tokens. And I know in the US you also have a lot of activities there. So. I guess the suggestion of Lukas to make sure we follow up on these activities and we kind of consolidate all the work is probably a good one.
Yeah, we'll try to have a follow-up meeting quite soon after this. Michael, go ahead.
Question to Ricardo, but actually also to our other speakers. When you burst to the public cloud, or if you're otherwise going across sites, how do you handle the data IO stuff?
Yeah, so most of the efforts up to now have been going on, at least from my side, on the compute. And this means that the data has to either be accessible remotely or be pre-populated there. So maybe Lukas even can comment a bit on this, but I know on US Atlas and Atlas in general, they've been doing a lot of work on making sure their dataset bookkeeping and movement service, Rucio, handles well public clouds as well, specifically the Google one, but I think there's activities with other public cloud providers. So I think if the integration of the analysis using Dask, for example, would rely on Rucio for the dataset distribution, the scheduling could take this into account as well.
Yeah, so that's definitely a concern. Maybe also touches on the question I had in the Slack chat, whether or not you can pin specific operations to specific workers, because then you might want to co-locate the operations with the data. I'm not sure actually if it's completely feasible to think of a Dask workflow that crosses different sites.
Yeah.
But yeah, I think it's a complicated issue. But
even for co-located submissions, you still have to have the data available there in advance.
Yeah.
But, yeah. So, but I don't think there's like a solution. Maybe the Ruchu people would be the best ones to say where we are.
Yeah, I mean, what's nice is that CMS is now also adopting Rusio as a data management layer. So definitely any type of solution that we come up with could probably be shared across different experiments. Is there any other question? So maybe one question that I had is, so one thing that is also not super clear to me is, so I mean, it's clear to me that using Kubernetes, we can definitely put together like a nice package like we have with Coffee Casa, that has like Jupyter Hub, it has some batch configuration and things like that. What's less clear to me is, okay, who is controlling the package? But then, if you have also Kubeflow, there's also Jupyter Hub in Kubeflow. There's like a workflow engine in Kubeflow and things like that. And so I wonder what the long-term strategy is. Do you have just like multiple Jupyter Hubs running alongside each other, or can you share the same Jupyter Hub and then have it modular that you kind of integrate it, or are these kind of siloed products at the Helm chart level?
I can answer quickly from my side. Actually, Kubeflow does not use Jupyter Hub. They used to. They replaced with their own native Jupyter environment deployment, and the reason for that is mostly security, because their product is Kubernetes only, so they want to have all the access control and authorization managed by Kubernetes. While in Jupyter Hub, you are actually delegating the Jupyter Hub tokens to Jupyter Hub, and you have to trust Jupyter Hub to manage that. But like from my point of view, I'm really interested that the infrastructure is consolidated, that we can deploy all these things in a consistent way in shared resources, and I think that's where Kubernetes is really like a massive gain. Then for the entry point, one thing we are working on, and I was thinking exactly the same question that you had. So we are working with Binder to be able to submit Binder builds not only to Jupyter Hub, but also to Kubeflow. So that would be one possible entry point, but it wouldn't be at the hub level. There are possibilities to submit to Kubeflow like pipelines from Jupyter Hub. That's fine. But yeah, we've been looking also at the integration with Binder.
Super, a lot of interesting features, Ricardo. I think, yeah, I will definitely write you or ask you more details. From point of view of Coffee Casa, we started it like a prototype, but now currently we are thinking about, because there is a lot of different requests. Like initially it was fully CMS. Of course, now there is idea to have open data. So for example, something that just support like training for the students. Then the idea is to have it like expandable. So we are trying now to trim out of everything that we have something more like a solid infrastructure. But our goal is basically not, we don't want to run everything in Kubernetes. We want to reuse all resources that are available somewhere already. So there was, like Carl told, there was spent millions of dollars, and we just want to, not spend again other millions of dollars. The other thing that we are trying to, since it is prototype and we have a lot of, possibilities to test interesting solutions. Like, for example, we definitely, we want to put Xcache in the Helm, to create a Helm chart out of it and put it as our dependency. Then we want to since we funded partially by Iris Hub. It's Iris Hub project. So we want as well to try to check out all interesting data delivery services. And so we want to have something highly modular, but at the same time, not to be afraid to, try all possible solutions and bring, because this is an interesting point. There is developed so many interesting software products, and actually wrapping them in Coffee Casa allows quickly to port it to any other environment. Yeah, sorry for the comment. Yeah.
Yes, I think, it's basically the same problem of whether or not you go very opinionated, because it's always a difference. Like some people have spent millions of dollars on the batch part, some have spent millions of dollars on the kind of interactive Jupyter part, and whether or not like you can kind of compose them together, or you either buy like the opinionated package from like A or from B is going to be kind of a difficult choice. But yeah, so we're kind of at the end of this very interesting workshop. I think it's clear kind of Dask also started to arrive in high energy physics, and yeah, I think there's enough interest that we're going to have a follow-up meeting, and we'll probably organize this, and if people outside of high energy physics are interested in joining, we'll definitely try to reach out and invite you. Certainly kind of also from astrophysics, we're interested in what the experience are there. We'll also of course go through kind of the talks that were shown at the summit generally. But yes, thanks everybody for connecting, and yeah, so we'll stay in touch. Is there anything else you want to add, Oksana?
Yeah, I just wanted to tell big thanks to organizers to allowing us to have these 2 hours, because it's probably first time that we are all talking in the same place. So it was amazing. Thanks a lot.
Great. Well, thank you everyone for joining today. The video will be available on the Dask YouTube after we get a chance to have that processed. So check the Slack to find out when that's going to be there. I know that everybody will probably want to revisit a lot of this because there was so much fascinating content. But otherwise, thank you again, and we'll hope that you enjoy the rest of the summit.
Yep.
Thanks.
Thank you.